Okay, I'm going to start. Welcome to ffE1a4l0nT4, lecture 25. Woo! Filter design. Okay, so we finished talking about... Hey! I'm talking now. There's a lot of things we have to go through. There's a few announcements I have to make, but we finished basically all the stuff about, so far, we've talked about all the transforms. We talked about the description, about discrete time signals. We talked about sampling, how you take analog signals, convert them into digital signals. We talked about the case where you've got band-limited signals, or what happens if you want to reduce the rate. We even talked about the idea of if you have a certain class of signals, can we compress them in the measurement stage and still be able to reconstruct them? So we went through all of this. We also talked a lot about, when we talked about wavelet, we talked about the multi-rate. We're always talking about filters, right? You want to filter your signal, filter it, decimate, filter. There's a lot of filter element there. And the real question is really, how you actually design one. We never talked about how to design a filter. Okay? When we talked about the Z transform, you just place zeros and poles, but it was all very intuitive. The question is how you design them, and this is what we're going to talk about today, and on not Friday. What's the first day after the weekend? Monday. Yes, that's right. Okay, so a few announcements. You're going to get who doesn't have the radios yet? What? Keynote Rush, right? Foursquare. Okay, so we're going to give you the radios and the interfaces immediately after the the class ends, or after the discussion. So you have to come to the discussion, and then immediately after. Okay, so the interfaces are really important to do labs 6 and 7. Okay. Now we have a problem. We've got actually too many labs that are coming up that we didn't finish. So we know you asked. So we gave you for this lab 4. We gave you basically almost 3 weeks to do this. Now there's some people that actually asked to get a little bit of an extension, but the problem is that we just it's just not possible. Okay. So we have to finish it before you have to finish it before. Now we're going to remove the last part of the lab that to be optional. So the mini project is going to be an optional part. So you don't have to do this if you don't want to. But I think it's really cool to go through. But we'd like you to submit this by tomorrow. If you don't submit it by tomorrow, then you would have to, if you want to get the full credit, then you have to do the mini project. So this is just, kind of an incentive for you to finish this. Now, lab 5 and 6 will be posted on Friday, and you'll have to do, lab 5 will be just simple compressed sensing. It's not going to be, too intensive, but so that will be due on Tuesday, and on Friday, that's lab 6, just again to test your radio. So it's not a lot of work. One thing I want you to think of, is, especially over the weekend, is to think about the projects that you're going to be doing. Okay, because we're getting to them, and the projects are going to be due the week. We said they're going to be the week of the dead week, right? The end of dead week, the project. Now again, because I put all the compressed sensing and the 2D material, there's really not enough material that we'll cover until midterm 3 where it's supposed to be. So we're going to do basically midterm 3 in finals week. Okay, so that's, I'm really sorry about it, but we really don't have a choice. And happy April 1st. Yeah, and nothing changes. There is a midterm on Friday, by the way. Yeah, all right. Okay, so linear filter design. Okay, just the real announcement. There is a midterm on Friday. That is real. The lab is actually, the mini project part is optional, but it's still due the day that it was supposed to. If you want to submit it by Sunday, you do need to do the mini project to get the full credit. So you get the 2 days, but you have to do a little bit more if you really wanted to. So that's actually, but that's posted on Piazza. So, okay. Midterm, third midterm is at the same time. Don't worry about it. And the rest will be okay. It's still going to be a lot of work, but yeah, we're not going to kill it. No. Not yet. I'm talking about the project. Okay, so FIR filter design. Filter design used to be an art, okay? It used to be an art. People, thought about how to design filters, and there's a lot of research about this. Today, there's really lots of tools that allow you to do optimal filter design. The thing is, you always need to pick an optimality criteria, and that can change the design completely. And whether you pick the right optimality criteria for your problem, that is a good question. Okay, sometimes you put specs, but that's not necessarily really what you are interested in. So again, whenever you do something optimal, and whenever somebody tells you that it's optimal, you have to ask optimal in what sense. Okay, so in some situation, it might fit your case, and it might not. Now, for DSP, there are kind of two common classes of filters that people do, and we're talking about linear filters, so not nonlinear filters. Okay, not adaptive. Basically, something that you can describe using a simple linear system, and we're going to talk actually about, a linear system. And then there's the infinite impulse response filters, IIRs. You did cover those in 120, so I'm not telling you something new. And there's those finite impulse responses, FIRs. Now, the thing is, although IIR is an infinite impulse response, it does have a finite degrees of freedom. Okay? So the parameters used to design the filters are of finite degrees of freedom. They're not arbitrary. Okay? Most IIR designs will be that way. I mean, that's how you pick them. Okay? So for example, they have a minimum or a certain number of poles that are allowed to be in the design. Okay? And so on and so forth. Though they'll have an infinite impulse response, it doesn't mean that there could be anything. Right? What we will cover for this class is we'll cover mostly FIR design, and I'll briefly talk about IIRs. But the reason for this is because these are quite useful. There are excellent tools that allows you to design this. In most cases, people use IIRs because they're less computational complexity, but computational complexity today is not as an issue as it used to be before. So in a lot of cases right now, still people are going back and using FIR designs. The techniques using to design IIRs are mostly based on the continuous domain that you basically kind of translate that into the discrete domain, whereas FIR designs are completely discrete, which I think are quite powerful in that sense. Now, what is a linear filter? Okay, what do we want from a linear filter? We want it to attenuate certain frequencies, so not pass certain frequencies. We'd like it to pass other frequencies. Okay, so that would be a pass band. We would like it to affect both magnitude and phase of the frequency. And phase will often correspond to a delay. Okay? when it affects phase, it often corresponds to delaying different frequencies by different amounts. You will see that mostly when we talk about the next chapter. Okay. Now, with IAR designs, the mostly nonlinear phase response. So the response of the phase and the frequency would be a nonlinear function. Turns out that a linear function is nice because it's a pure delay of the of whatever is input. Okay, you put an input at a certain frequency, you'll get a pure delay of that output at all frequencies. And nonlinear response creates this dispersion, where different frequencies are delayed by a different amount. Now, IAR, some of them, when you design them linear over a certain range of frequencies, but you can't really do that over all ranges of frequencies. With FIR, it's much easier to control the phase when you design them. And you can design either a nonlinear phase, but also completely linear phase filters using finite impulse response. Okay, so that makes it very, very powerful because this is really, really useful filters. Okay, that you don't see the distortions. At the same time, there is an advantage of using nonlinear phase. So you can get sharper selection of frequencies for a lower order, for example, but you trade off this dispersion, right, or the distortion that you might get into whatever you're putting in. Okay, you'll get it more as we talk more about systems and what's the phase response and what's and so on and so forth when we talk about linear phase and type of systems in the next chapter. But phase is kind of a hard concept to digest. Okay? I deal with phase almost daily because MRI is all about phase. Okay? But it takes time for people to understand kind of what phase means. Okay? But phase, you can think of it as kind of like delays and where things appear. Those are contributed often by phase. Okay? Now the question is like, okay, so how do I design a filter? Right? I want to pass certain frequencies, a certain amount. I want to attenuate certain frequencies. But how do I design it? What do you think? I mean, ideally, what would I like to do, right? I mean, ideally, in the ideal case, let's say infinite time, I can compute things in the continuous domain. I mean, what could I do? How do I design it? Especially if we want to prescribe something in the frequency domain, yeah. Draw what frequencies you want, right? So ideally, I mean, I have a certain frequency response that I would like my filter to have, and I will just apply it, right? Yeah, I can do that. The problem is that if I just draw it, on the continuum, I mean, like how do I am actually going to implement it? What are going to be the associated memory requirement, delays in the system, complexity, and all sorts of things like this, right? Now we're going to talk about finite impulse response filters, right? So when I talk about finite impulse response, I could draw the impulse response that I want as much as I like. But obviously, the result will not have necessarily a finite impulse response. So what I will need to do then is to approximate. I'm going to approximate my desired impulse response through a finite set of filter taps, right? That we will convolve our signal with. Okay, that's the whole idea about finite impulse response. And I'm going to decide what is the order of my filter. I'm going to have a certain frequency response I'm going to have, and I want to try to find the coefficients of those filter taps, let's say 16th order filter or 256th order filter, that would match my criteria the best it could, right? That would be optimal. But what we're going to do is first talk about a very simple method that's quite used now. It's not optimal in any sense, but it is very easy to do, and you've seen a lot of people actually still using this particular design. And this is FIR design using windowing. Okay. So the idea there is that I have a desired frequency response, like you just said, which is going to be h sub d eta j omega. Okay? So this is the discrete time Fourier transform, the ideal one that I'd like to approximate. And then I'd like to find, what I'm going to do is I'm going to find the impulse response corresponding to the ideal. And then I'm going to try to approximate that impulse response by taking an mth order causal filter, okay, that approximates that ideal frequency response. Okay? By basically truncating the impulse response and windowing it. Okay? So if this is the ideal impulse response, the actual impulse response of the filter, or my FIR filter taps, are going to be the desired impulse response multiplied by a filter. And that filter could, by a window. And that window either could be rectangular window, it could be Hamming window, Kaiser window. And that's going to, of course, implicate of how well my frequency response is approximated. Okay? But if you think about this, it's really just taking an inverse DTF. Like I want to design something, I'm going to design it. I'm going to take an inverse DTFT. Okay, so I'm going to go from continuous to discrete, and then I'm just going to crop it. Okay? Sounds reasonable, right? But what are the implications of cropping it? We kind of went over this. What is the implication of cropping a part of a signal? Remember when we talked about, time frequency analysis, or actually frequency analysis, right? When we crop a signal, just part of it, what do we have? What are the implications to the frequency domain? You convolve with something. It depends on how you crop, right? Because we're going to window. So you convolve with some spread function, right? And we're going to have, so basically the frequency response is going to be blurred. And it's going to have some ripple, right? So we're going to deviate from the ideal. Okay? So whatever I'm going to tell you right now, you've seen it before in terms of frequency analysis. Now you're going to see it in the terms of design. So it's not analysis, but the other way. Like we want to design something to have particular criteria. Okay? So we already saw that when I crop, or I window a signal, or I window, in this case, the impulse response, what I'm going to get is a convolution. Is that a convolution? Periodic convolution. $1 for me. Okay. It's a periodic convolution between the desired frequency response and the frequency response of the filter, of the window. Okay? So for a boxcar rectangular window, okay, if I take a window that is, of course, causal, okay, so it starts at n equals 0 and then goes to up to m, of mth order, which means that it's going to have m plus 1 number of values. Okay, so mth order is m plus 1 number of values. Remember this. We're going to use it quite a bit. Okay, then it's going to have a frequency response, which is basically a linear phase of m over 2, because it's causal, so it has to be shifted. And then this is a periodic sink, right? This is a periodic sink. A boxcar or a rect function in the frequency domain is a periodic sink, and because now it's not centered around 0, it is shifted. It it is causal, then it's going to have also a linear phase component. And what is the, how fast this periodic sink oscillates? Well, that depends on m, on the order of it, right? Okay, how squeezed it is. So in the case of when I have this desired frequency response that is just a low-pass filter, okay, that filters, let's say, half of my frequencies and passes, the other half. So passes the lower half of the frequency domain and then doesn't pass the other ones. That will be convolved with the Fourier transform, basically with this, which is a periodic sink that has a magnitude response and a phase response. Okay. How does this phase look like? Is it linear? Is it a linear phase? Why is it so jagged? Why is it jagged? Yeah. Wraparounds. I only see one wraparound. I see here. That's a wraparound between minus pi and pi. But these ones are not supposed to be wrapped. Right. The sink changes its sign. When I take a magnitude, everything becomes positive. So all the sign changes go to the phase. Okay? I could have drawn it as a sink here, and then I would not have these pi changes. Okay? If I drew a sink with a negative positive lobe, then the phase component would not have these pi jumps. Okay? Pi jumps is a sign jump. Okay? So it's a little bit confusing when you first see it. It's like, wait a second, why do I have these jumps? Are these phase wraps? No, they're not phase wraps. They're representing basically the sign changes of the sink. Okay? All right. So this is convolving this, which will give me an approximation to this ideal frequency response, which is a little bit blurred. So there's now a transition band. It's not as sharp anymore. There's also ripple, both in the pass band and the stop band, that approximates it. And I can get a better approximation if I, for example, use m to be larger, right? If m goes to infinity, then I will get a sink, right? Almost. If I will take m to go to infinity, then it almost will be looking like a sink. Okay? Sorry, not like a delta. Sorry, it will look like a delta function if m goes to infinity. This will more look like a delta function than a sink. Okay, everything will be squeezed and squeezed and squeezed, and the side lobes will go lower and lower, and then squeeze, 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 and then it would more look like a delta function. Okay. All right. So we have bandpass filter. We've got a transition width, and we've got stop band ripple, and this would be the ideal. And so making the approximation makes me deviate. And that's always going to be the case. There's always going to be this trade-off between the length of the filter and how I can approximate the frequency response. There's always going to be a trade-off. Now, I don't like this ripple. How do I control the ripple? The ripple is quite annoying, right? I mean, definitely not attenuates those frequencies. Use a different window than erect, right? We've seen that before. If you want to drop those ripples, how about we use a smoother window? What would be the result of using a window, like a smoother window? It's obviously going to be a trade-off. What's the trade-off? Transition width increases, right? Transition width increases. Passband ripple will reduce, but transition width increases. So if I want to make a sharper filter, what do I need? More taps, right? Same thing as the frequency analysis, right? So I can kind of move on, right? So I can use, here's slides from lecture whatever frequency analysis one. I can use a Henn window, I can use a Henning window, I can use a Hamming window, I can tell you all the story about all these windows, but I'm not, because I already told you them. Okay? And the good thing about this is that, for different windows, you'll see, this thing decays the window decays pretty rapidly. You can see how much ripple you get and so on and so forth. So for your particular application, you can choose the right window that will be best for your application for your particular number of taps, for the minimum number of taps. Okay? And Python has scipy.filter.firwin. This is a function that uses exactly this window approach in order to design a filter. MATLAB has FIR1, I think. Right, FIR1. I think that's the filter design that uses a window. Okay, that's the function that generates it using a window. By the way, I have to mention, filter design is my favorite topic. It is. I'll tell you later about why. Yeah.
So, like, for filter between the tabs, what is the length between the tabs?
Oh, taps, I mean just basically number of elements. Okay, so we're going to take a window, like an m equal 15, we'll have 16 taps. Because it's always m plus 1 we're going to be using. Okay.
So what's the time between the two tabs?
I don't know. It's digital. Who cares what the time is? If you want to figure out what it corresponds to a continuous time signals, you need to tell me what the sampling rate is, right? Then you need to do the translation yourself, okay, what the sampling rate is. Okay? So that's kind of the idea. How's spring break? Was good? Yeah? Did you guys refresh yourself? Are you guys less tired? No, me neither. That's okay. That's okay. That's what school is all about. Tire those bright young minds that they don't do crazy stuff. That's the idea. All right. It may be useful to society as well. All right. So how do you design? Okay, but we need a procedure. We need an algorithms. How do you design? Write a function. Write a function. Mickey, write a function. Filter design. Okay, how do I do this? Well, first thing I do is I choose a desired frequency response. I chose it. Okay? I'm going to choose a non-causal, what's called a zero delay, so like without phase, effectively. I don't want to design and think about the phase and stuff. Usually, I've just, one that it's not delayed. I'm going to delay it afterwards just by adding a linear phase to it. But when I design, I don't want to think about this. Okay? So the linear phase just adds basically a delay afterwards, so I don't need to care about it. So a zero delay filter. If we think of a, just a low pass filter, I would just design it as a box. Okay? Pass high frequency, low frequencies, attenuates low frequencies, right? And without the phase. Then if I know what my filter length is, I'm going to add the right delay. Okay? So I'm going to compute the non-causal, zero-delayed, infinite impulse response filter, okay, in the frequency domain. Now, if it's derived from continuous time, I have to choose a t, okay, like a sampling rate. If I choose a sampling rate, then that will give you the right omegas. Okay, so you have to think about, if I have a frequency that I want to make the the stop band, I can pick pi over 2, or I can relate it to the continuous time depending on my sampling frequency. I'm sorry that I'm watering you. Sorry. Look, spit's going out. I apologize. This is just an exciting topic. It's like I'm so thrilled to tell you about this. I'm really is, actually. Really am. It's not even because it's April 1st. It's my favorite. So now what I need to do is I have this desired, right? And I can derive it from continuous time. I can relate it to how it is. Then I'm going to pick the length of it. And the length of it is going to be m plus 1. So I'm going to pick an m, and the number of taps is going to be m plus 1. Okay? That will affect the transition width of the filter. Okay? Then I'm going to pick the type of window. Henning. Just pick one. Okay? Probably not a rect. Okay? Because just too much ripple. that will give me the also transition width, but also the amount of ripple. So I will get some more transition width, but much less ripple. The trade-off is more favorable there. Okay, once I picked M, I know the linear phase that I need to add in order to make it causal. Okay? Because now it's a certain order, so I need to shift it such that the first step hits 0. How do I do that? I add a linear phase with the amount M over 2. Okay? That will shift it such that it will be causal. This is why it's easy to do. Okay? So that's why we don't consider it up front. Okay? So simple. Choose this, choose that, choose this, choose this. Now I got it. Okay? Now I'm going to compute the truncated impulse response. Okay? So I'm going to take the inverse dTFT of this linear phased filter, and I'm going to compute it only between 0 and M. Okay? All right? Then I'm going to apply a window. And the window that I apply is going to, again, depend on the window that I picked. Okay? This is already applying a rectangular window, and then I can just add an extra sweet Hamming window to taper off the rough edges of this filter. Okay? All right, once I did this, I'm going to verify that it meets my specs. I'm going to compute back the frequency response, and if it doesn't meet the specs, I need to do something about this. I can either make the order of the filter longer, I can change the window, or make the order of the filter longer, or change the window, right? Or make it longer, right? Worst case, you can change the window, but really you can just make it longer or change the window. There's not much room really to play here. Not that many degrees of freedom. Okay? And then you're done, basically. It's very simple. This is why it's a pretty effective type of filter design, I have to say, because it gives you a good filter, a relatively good filter, and it's really easy to do. But definitely no excuse if somebody actually uses it. Because obviously it doesn't make sense that you'd like to use this. I mean, well, people use it all the time, in particular yours truly, if they don't really care so much about the filter. But really, when you filter, you should really be caring about what you filter out, what you filter in. Okay. So here's an example for a low-pass filter. For a low-pass filter, my desired will be 1, anywhere up from 0 all the way to omega sub c, and then 0 otherwise. Okay. And then we're going to choose M, and then compute H1, which is basically the linearized phased filter, linear phased filter. Which then if we look at the impulse response, and I found my typo before you. These were all handwritten slides up to 2 days ago. So, okay, small h1n, which is basically just a periodic sink. No, it is a sink. Okay, it is basically a sink that is cropped. Okay, because of course, if I take a rect in the frequency domain, the inverse Fourier transform will be a sink. Okay, it's a shifted sink actually, and it's shifted by m over 2. Okay, it kind of makes sense. If I want something rectangular in the frequency domain, I will get a sink, a discrete sink, not a periodic sink, a discrete sink in the signal domain. Okay, so it is a sink, and you can write this either this way or this way. All right. So this is also called a windowed sink filter, right? Because if you want a box in the frequency domain, then of course you're going to take a sink and you're going to window it. And so this is the windowed sink design. You window it by a certain window, and that's pretty much it. And yeah. Where? This one? No, it's Bandas. I did it on purpose. Remind me last name? Morton? T-A-N? $1. You're getting better. I'll give you more opportunities for new slides. Okay. So you design. So this is a low-pass filter design. Basically, you take this discrete sink and then you window it. That's it. Window with a Hamming window. Basically, that's all you need. And you need to know, based on omega C and M, that basically squeezes the sink or shifts it around. That's pretty much what it is. Okay? So it's very easy to design. Now, if you design a high-pass filter, what you do is you design a low-pass filter, and then you can modulate it. Okay? So you can modulate it by plus minus 1, which basically takes the low-pass into a high-pass. Okay? So that's the easy. And if you want a band-pass or a band-ass filter, then you basically modulate by a cosine. Okay? So if you modulate by a cosine with some omega 0, that will shift the frequency response to the right band. Or if you want just a one-sided filter like you are doing in your lab as we speak about, as I talk, then you just modulate with a complex exponential. Okay? So that's a one-sided bandpass filter. Okay? That's pretty much it. Any questions? Easy, right? That was easy. Yeah.
You guys are pretty slide because you're multiplying by e to the power j omega m over 2.
Yep.
Are you doing that to make the impulse response causal?
Yeah, I'm making the impulse response shift by m over 2, and then I'm going to crop m plus 1 samples out of it. From 0 to m. I'm going to crop. Yep.
Okay, I get that idea.
So it moves the center of the sink to the middle.
Don't you want to move the center of the sink off like the positive side? You don't want any negative.
Yeah, I'm going to crop. So whatever is negative, I'm going to start from 0 all the way to n. Okay. But now my sink is in the middle.
Okay.
So it's always I'm going to get the sink in the middle of my signal. That's the idea. Because if I cropped from 0 to m and I didn't multiply by the phase, I'm just going to have a half a sink, which is not a good thing. Remember the half sink that didn't work for us before? Remember I told you about, you remember the homework question that you had? You didn't put the linear phase, you just, compute stuff, and there was like a terrible filter. The filter that you designed in the DFT domain? Remember? I described like how really bad the filter it was because we didn't have the shift. It was like half a sink doing. Anyway, go back a few lectures ago. It's a terrible filter. Okay, so what I'm going to teach you now is not in the book, but super useful. Okay? It's characterization of filter shapes. The term time product bandwidth, I have not seen it in the book. If you find it, let me know. I don't think it's there, but maybe it's there. I'll give you $1. It might be there, but I'll give you $1 anyway. Right? So a time bandwidth product is a unitless measure of time multiplied by bandwidth. Okay? No. Do I have a... Is like bandass again or something? Is that embarrassing? It's what? Which one? Where? Yeah, it's a unites measure. All right. What I think is, there's not just words, and so I think it was the correction. The autocorrection. Apple. All right. So this is a uniteless measure. What it is the time. So whatever filter you do is going to have a certain time you're going to apply it on, okay? Corresponding either to, in the discrete, to number of taps, or to the original continuous time domain to the length in time. And it's going to have a certain bandwidth that you're going to pass, okay? And that's going to be either in radians or in hertzes, okay, if you think about this. But it's going to be unitless because when you take time and multiply by bandwidth, which is inverse time, then it has no units. But it tells you a lot about how the shape of the filter looks like. Okay? So time times bandwidth, in that case, will equal to n plus 1 multiplied by omega over 2 pi. Okay? That will be unitless. Okay? If it was just omega, then it would be radians. But I don't want to deal with radians. Omega over 2 pi is unitless. Okay? What it also turns out to give you, in the case of the slow-pass filter, is the number of zero crossings of the sink, or the windowed sink. Okay? So time bandwidth 2 filter would look like this. So we just have a main lobe. Time bandwidth 4 will have one. Is that time bandwidth 4? Yeah. 1, 2, 3, 4 zero crossings. Time bandwidth 8, 1, 2, 3, 4, and 4 on the other side, and so on and so forth. So what it really tells you is, if I tell you I'm going to design a time bandwidth 8 filter, you immediately can imagine in your head how that filter is going to be. It's going to look like this. Something like this. Maybe stretch, maybe, but it's just going to look like this. Okay? The larger time bandwidth, the more sync function it's going to look like. Okay? So the more you increase it, the frequency response will more look like a rect function. Okay? Would look better, like more rectangular, sharper transitions. The higher the time bandwidth is, Okay? So in the case of time bandwidth 2, and n equals 16, this is my low-pass filter. Okay, it's not very selective. Time bandwidth 2 is not very selective. It's more spread out. When I go to time bandwidth 8, now it's a little bit more kind of shape is a little bit more kind of selective. But because I kept the same n and I increased the time bandwidth, if the n is fixed and I increase the time bandwidth, what changes then? The bandwidth, right? So now the bandwidth is increased by a factor of 4. Okay? So my bandwidth increased by a factor of 4. And now what happens if I increase both? Both by a factor of 2. I get the same bandwidth, but it's going to be a sharper filter. Okay? So time bandwidth 16 and n equal 32, or m equal 32, will be just a sharper filter, okay, on the same bandwidth. What if I go for time bandwidth 32 with n equals 64? It's just a sharper filter, right? And so on and so forth. So I made this IPython notebook for you that you can actually go and try it if I can find it. Oh boy. Yeah, there it is. There you go. So with this IPython notebook, I can kind of change. Oh, great. Right. I can change the time bandwidth, and then you can see how the filter becomes, more of a sink. And then because n is fixed, I'm increasing the bandwidth. Or I can go and change n for the same time bandwidth. The shape doesn't change, but now my filter becomes, wider and wider, but it's less selective, and so on and so forth. where time bandwidth 2 is the least selective one. Okay, so even if it's really, really long, then look what happens. All right? So this is a very useful type of analysis of a filter. And when I give you just parameter, this parameter is really useful to give because here's an example. What are the length of these filters in this filters in samples? Let's say this is a filter that filters between minus pi over 12 to pi over 12, and I know that it's time bandwidth 2. You can immediately know the order of the filter that you want. Okay, it's really easy to design a filter based on this if you think about it. Okay. What is it? So 2 equals what? M plus 1 times, what's the bandwidth? Pi over 6 divided by 2 pi, right? So the question is like, what is M? So M plus 1 multiplied by pi over 6 divided by 2 pi, that equals 2. In that case, M equals 23. Okay? So if I pick a 23 length filter, then it's going to pick that. Okay? If I want a sharper filter that filters pi over 12, up to pi over 12, minus pi over 12, then I will have to increase my length. Okay? That's the, time below time bandwidth 2 is just not possible to get like something that's selective. So if I really want a sharper filter that filters this narrow band, I'll have to increase the length in order to make it sharp. There's just no other way. That's the the narrowest filter I can use. Okay. What about this one? Time bandwidth 12. Turns out if I take this is a pi bandwidth, then in that case is also M equal 23. So if I increase the time bandwidth now, then it's wider. If I want that to go back and look like this, but only sharp, then I need to increase M by a factor of 6, right, in order to get to make it sharp. So a narrow band filter costs if you want to make it a high time bandwidth. Okay? Do you see the point? It costs in length. If you want to make something really selective, if you want to make it a high time bandwidth. Okay? Okay, so any questions? Yeah.
What's the unit of M?
The unit of M, samples.
So like samples times frequency is unitless. I thought like you have to compute time.
Samples times frequency divided by 2 pi is unitless. Right? What's the frequency? It was radian, right? Inverse radians, right? Yeah. So it is unitless. It's cycles per, right? Because you take samples, that's the time, kind of for discrete, just samples, right? N, and then that is converted into omegas after the Fourier transform. Okay, so it is unitless. All right. Just before we finish, the next thing we're going to talk about is optimal filter design. And so the window method is really kind of a heuristic, right? It's not optimal in any consideration, right? It gives you a certain transition for a particular case. But what if I have a more complex filter that, what if I'm okay allowing like a much larger transition? I really want to be really flat in a certain area, and I don't care about certain other areas, and I care about attenuating certain frequencies. Can I do better than using the filter method? And the answer is, of course, you can. And for those taking 127, when talking about optimization, that's a lot of things tools that you'll be using. So in the case of optimal design, you want to find a filter Hn with a certain frequency response such that it approximates the desired one with an optimality criteria that satisfies specs. And just to lead you to what we're going to talk about is an example where you have some passband and you want to, certain frequency that you want to pass, there's certain frequencies you want to stop, but you don't care about the frequencies in between. And the question is like, how do you design the best filter? And what is an optimality criteria there? And so one example of an optimality criteria would be mean square error, for example, or square error between those, right? But you can have also a maximum deviation, right? Or a min-max error. You want to minimize the maximum deviation. Or there's maybe other criteria that you'd like to design. Those will result in different filters, okay? So that's what we're going to talk about next time, right? Now, I forgot to say, actually, and this is real, not April 1st. I am not going to be here tomorrow and on Friday. I truly apologize. I'm not going to be here, right? But if you have any questions, please forward to the TAs, and best of luck on Friday. Okay, so go get your radios.